All right, and with that, I would like to introduce our afternoon community kickoff keynote by Miss Samantha Quinones, and she's going to talk to us about how PHP got its semicolons. Yay!
Okay, can we very quickly give a round of applause to Heather and Eli and the One for All crew and the PHP Architect crew, because they're amazing and they killed it again. For those of you who don't know me, obviously I need to do a better job with my Twitter branding. My name is Samantha Quinones. I'm a software engineer. I'm not going to put up a vanity slide. Instead, you can look at my adorable children who are amazing. We're here tonight to talk about community, and I want to do that by talking about where we came from. When I say we, I mean we as the community of software engineers, not just we, the PHP community. In addition to the things that I do with computers and the things that I do with bikes and the things that I do with blowing air into a microphone to make really, really noises and make Tim mad at me, I am an amateur computer historian. I believe that we have to look to the past to understand the present and understand the future. I love this quote by Alexis de Tocqueville. When the past no longer illuminates the future, the spirit walks in darkness. So I think it's always important to look back. And I want to look way back. I'm going to tell this story of where our community came from, and I promise I will answer the semicolons question. I know it's on everybody's printed schedules. I will answer that question. It'll blow your mind. You won't believe what happens next. Ada Lovelace. Ada Augusta King Knoll, Countess of Lovelace, excuse me, I want to be formal, was born in 1815. She was the illegitimate daughter of Lord Byron and Anna Milbank. And she was what we would recognize today as a mathematics prodigy. She understood advanced mathematics by the time she was a young teen. A lot of this was helped by the fact that her mother, Anna Milbank, really encouraged her to study math, which was not very common for young women of the time, especially young women in the aristocracy of the time. But her mother felt that by studying mathematics, that might help temper the passions that she may have inherited from her poet father. So when she was 18 years old, she was already a very well versed mathematician, and she met Charles Babbage through sort of the aristocratic circles of London, and they began corresponding, writing letters back and forth about Babbage's analytical engine, which was a theoretical machine that was capable of doing arithmetic computations. Right, completely theoretical. It never got built. He gave a lecture about this machine in Turin, a very famous lecture, and Ada Lovelace was engaged to actually translate that lecture from Italian into English. And as part of doing that, she really undertook to understand this machine and added a bunch of her own notes about this machine. And included in these notes, she actually wrote out algorithms for doing certain things, like computing Bernoulli's numbers, right? So she was actually using this theoretical machine and writing algorithms for it. She realized that this machine was not only just capable of arithmetic, but it could actually solve any problem of arbitrary complexity. She wrote the analytical engine might act upon other things besides numbers, were objects found whose mutual fundamental relations could be expressed by those of the abstract science of operations, and which should also be susceptible of adaptation to the action of the operating notion and mechanism of the engine. Supposing, for instance, that the fundamental relations of pitched sounds in the science of harmony and of musical composition were susceptible of such expression and adaptations, the engine might compose elaborate and scientific pieces of music of any degree of complexity or extent. This is the 1830s. She's talking about computer-synthesized music on a machine that doesn't exist. Welcome to she was, it's ridiculous to say she was ahead of her time. This is 100 years before the first practical computer would be built. 150 years before computers could start composing music on their own, which is the thing that we're just now starting to see happen. Her contributions to computing were lost for a really long time. She was just that far ahead of things. But they would be rediscovered later, and we'll come back to her briefly in a little bit. But I want to talk to you about a very important inventor. His name was Herman Hollerith. He was born in 1860 to German immigrants, so just before the Civil War in the United States. And he went to MIT. He actually ended up teaching mechanical engineering at MIT, and he was a builder of tabulating machines, so machines that used punched cards. Like, punched cards have been around for a long time. They were used to control looms in the 18th century, but he figured out ways to kind of use these cards for tabulating, and actually came up with this pretty revolutionary notion that you could record statistical data, any statistical data that could be represented as an on or off value. Does this sound familiar? An on or off, or true or false value, by punching a hole in a punch card, like you would use to control a loom. So to give you some context, for those of you who aren't from the United States, or even some of you who are from the United States and aren't aware of this, we conduct the census of the United States population every 10 years, as is required by the Constitution. And in 1880, the census recorded a population of 50 million people in the United States, and they didn't really know that until 1888, because that's how long it took to crunch the numbers. Using early tabulating machines built by Hollerith's company in 1890, the 1890 census recorded a population of 62 million people, so a 12 million increase, but it only took 6 years, which doesn't sound like much, but that's a pretty big increase in performance, right? At the urging of some of his business partners, Hollerith developed this mechanism and eventually expanded it to use electrical connections to increment counters. This allowed them to use punch cards to record real data. A key idea was that data could be recorded by the presence or absence of a hole at a specific location, and he organized these cards in rows and columns. Right? So whether or not a card was actually punched out or not could be detected electromechanically. And by knowing the position of certain bits of data on each of these punched cards, and you can see one kind of here in the front, you could electromechanically sort and count the data on those cards. His company is called the Tabulating Machine Company. The Tabulating Machine Company got caught up in the early part of the 20th century in an amalgamation of a number of companies that were doing this thing, and became this monster company called the Computing, Tabulating, and Recording Company, which is kind of a mouthful. So they changed the name to International Business Machines, which you might know as IBM. I told you I was going to come back to Ada Lovelace, and I'm going to come back to her through another Brit, Alan Turing, who was born in 1912. His father was a civil servant. He attended public schools, which I understand is the British way of saying private schools, because the English are weird. His teachers were really concerned because he wasn't interested in the important things he was supposed to be studying, the classics and Latin. He was way more interested in math and science. He was another math prodigy. During his time in university, what we would call an undergrad today, he did really pioneering work on the theory of computability, which was at the time a brand new science. He provided a proof of the central limit theorem, which was a mathematical problem that had plagued mathematicians for a very, very long time. So he was not bright, not smart, not a good student. He was a genius. He was a prodigy, a math prodigy. He reformulated Kurt Gödel's theory of computation and proposed this theoretical machine, another theoretical machine, that could perform any computation as long as it could be represented as an algorithm. Now, does that sound like someone else using a theoretical machine to do any arbitrarily complex computation? That machine, that conceptual machine, is what we call a Turing machine. People have built things that are kind of pseudo-Turing machines, but the idea here is that you have a machine that operates on an infinite tape that's divided into cells. So the machine positions its head over a cell, and it reads whatever's there. You look that symbol up in a table, and then based on what you find in that table, you can move to the left, move to the right, erase the value, replace it with another value, write something. Right? So this machine, in theory, given a finite set of instructions, can compute any computable problem. So any problem that can halt can be computed. Right? So when we talk about modern programming languages, one of the things we talk about is them being Turing complete. Just to say that given this finite set of instructions that makes up a computing language, can it compute any computable problem? And if it is, we say that it's Turing complete. PHP is Turing complete language, right? During World War II, he joined the Government Code and Cipher School. This is part of the effort to break German encryption. He made really important improvements to the Polish Bomba machines, which were machines that attempted to brute force German cryptographic machines by literally mechanically incrementing through every possible combination. So the Enigma used 3 cylinders essentially to set random values as a key. So it attempted to just brute force that. It wasn't super effective, but it did work. He later turned his attention to the naval Enigma machine. There was the Germans used these Enigma machines in all branches of their military. But because of the problem that you have communicating with ships at sea, especially submersible ships at sea, they couldn't rotate their keys long enough, and that put a vulnerability into their cryptography, which made it a little bit easier to break. Essentially, he built a machine that could take a piece of likely plain text, so you kind of guess at what they might be transmitting. And by using the probability that any 2 given pieces of text are going to see characters repeat in a predictable way, would then compute possible ciphers until you came up with a contradiction. So it would run through ciphers and it would say, oh, okay, we found a cipher, we found a set of settings for the Enigma machine that can't be set, so we can ignore it. And that cut down the number of possible settings that you had to feed into the Bomba machine to run through brute force by an order of magnitude. So it made the Bomba machines much more effective and led to breaking the Enigma machines, at least for the German Navy. His story then takes a very sad turn. At the time, homosexuality was illegal in Britain. It was until shockingly recently, 1960. So less recent than Texas. Pew, pew. He was convicted of homosexuality in 1952. He pled guilty and acceded to being chemically castrated. And 2 years after that, he died, most likely by suicide through poisoning. But he also brought back Ada Lovelace's work. So not only did he contribute in immeasurable ways to computing by himself, he also kind of helped us rediscover this longer legacy that we have. So while we're still in the war, Jean Bartik was born in 1924. She attended a teacher's college and majored in mathematics. In fact, she was the only student awarded a mathematics degree in her year. After college, she joined the U.S. Army as a computer. So that may sound weird, but prior to the dominance of the electronic computer was a term that was applied to people who computed values. In this case, she computed ballistics trajectories, meaning for a given gun, compute all of the possible angles you might need to point that gun at to get the projectile to a certain position, given wind speeds and wind directions and all this stuff. And you compute all of this stuff by hand using a mechanical adder and put it into a table, and you give that to the Army, and then the ballistics firing crews in the Army can then use that information to point the gun in the right way and hopefully hit the thing that they want to hit. At the same time, the US government was pouring a lot of money into this thing called ENIAC, which was an electronic computer meant to do the same thing, and they built this amazing piece of hardware. And they said, look at this amazing metal machine that we have built. Let's find someone, I guess, to program it, I guess? I don't know. Jean and her colleagues were brought in to program the ENIAC, and they were not actually allowed to access the machine itself. They had to figure out how to program this machine from the hardware schematics, from the wiring diagrams, finding places to work where they could. No one had ever programmed a computer before, so think about like the most basic things in computing. Even if you're writing assembler code, you have conditional jumps, you have if statements. No if statements. All of these very, very primitive operations that we take for granted in programming came from Jean Bartik's team. The idea of subroutines, what would eventually become functions, jumping to someplace else, running some code, and coming back. Right? Control structures, ifs, loops, nesting control structures within other control structures. So thanks to the programming work that they did, they built a machine. They built this machine and then programmed this machine. It could compute ballistics trajectories 1,000 times faster than the other kind of machines that were being used to do this. And Jean Bartik once bragged that the machine could actually calculate the trajectory of a bullet faster than the bullet could travel along that trajectory, which is pretty impressive. She worked with John von Neumann, converting the ENIAC to a stored program computer. She also then went to work at Remington Rand when they took over Eckert Mauchly, who was working on the UNIVAC 1. This is programming. Kind of looks like my code. So she worked for Remington Rand for a really long time. Eventually, her husband came to work for Rand, And she was not allowed to work at the same place that her husband was allowed to work at. So I guess being fed up with Rand, and this is me editorializing, fed up with the patriarchy, she pieced out for about 16 years. But she did a tremendous amount of work with her team to define what it is to program a computer, trained the first legions of programmers for the U.S. Census Bureau that brought those census recording times down from years to months and eventually weeks. So someone that Jean came in contact with through her work on the UNIVAC was Grace Hopper. Grace Hopper's a personal hero of mine. I literally have a poster of her in my living room. She was born in New York City in 1906. She was rejected from Vassar College at age 16. So again, kind of a smart person because her Latin scores were really bad. She eventually made it in. She got a degree in math and physics and then went on to get a PhD from Yale. After that, she joined the Navy during the war as a wave. And she worked on the Harvard Mark I computer, one of those other ballistic trajectory computing computers that the ENIAC blew out of the water. She eventually joined Eckert Mauchly working on the UNIVAC 1, which is where she came into contact with Gene Bartik's team. But she worked on building compilers, which was kind of a weird thing at the time. Like you wrote code by, in this case, like in a lot of cases, like actually moving wires physically on a patch panel, or maybe inputting machine instructions in hexadecimal that would get recorded into core memory. She had, in 1952, built a compiler, and she said nobody believed it. Like, I had this running compiler, and no one would touch it. They told me computers could only do arithmetic. She would go on to create a language called Flowmatic, and Flowmatic led to the Codicil conference, where she led a team that created a language called COBOL, which you can see here on the screen. This is FizzBuzz in COBOL. COBOL is the most ubiquitous business language to date. COBOL runs pretty much anytime you use your credit card to purchase something. If you book an airline ticket, some COBOL code is being executed. Some of that code hasn't been touched since the late 1970s. But it's out there. And not only did she give us this language, she really brought the idea of a language. Like, this is something that you can read if you're not a mathematician. You don't need to understand hexadecimal machine instructions to read this. She was retained by the Navy way beyond the mandatory retirement age. In the 70s, she started to advocate for replacing monolithic systems with distributed systems, so way ahead of her time. She was largely responsible for kind of pushing forward the NIST standards and like standardizing programming interfaces. She's also responsible for another one of my very favorite quotes. I try to live my life by this. It's easier to ask forgiveness than it is to get permission. I take that as a command to just be bold and do things when you think that they're right. And if someone gets mad at you, you can always say sorry. Who knows? So I think that's probably like the most famous ones. Who knows John McCarthy? Lisp, yes. Born in 1927 in Boston. He taught himself advanced mathematics from a textbook, so another smart dude. He got suspended from Caltech because he wouldn't go to his phys ed classes, but he did eventually get his bachelor's degree after serving in the Army. He got a PhD from Princeton, taught at MIT, where his professors referred to him as Uncle John. He was one of the founding fathers of artificial intelligence, along with Marvin Minsky and Herb Simon and Alan Newell. And he worked on Lisp. He created Lisp, which became the standard language for AI development. It is also the predecessor of languages like Scheme, which you may not have heard of, and JavaScript, which I'm guessing maybe you've heard of. And he also worked on a language called ALGOL, which I'll talk about in a little bit. One thing that I find really interesting about this is if you look at Lisp, who knows what this is over here? Who recognizes this language? Cold Fusion. Cold Fusion is a derivative language from XML. XML is a derivative language from Lisp. JavaScript and Cold Fusion, like first cousins. A lot of the terminology that we use in object-oriented programming came out of Lisp and out of Simula, which was a descendant of Lisp. So the idea of objects. Lisp had these things called atoms, which had attributes, things that we would recognize as objects. I was talking about ALGOL. John Backus was born in 1924 in Philadelphia. He studied chemistry at UVA, but he dropped out, got drafted into the Army, served in the Army, came out. Then he studied medicine at Haverford College, but he had to drop out of there because he got a brain tumor. But then he got better, and he studied as a radio tech, and he got a bachelor's degree. Then eventually he went to Columbia University, got a master's degree in math, and he joined IBM, where he wrote a compiler. He actually created a language called speed coding for the IBM 701, which was the first high-level language for an IBM computer, right? Which is a pretty big thing, because IBM computers were not meant for research. They were not meant for the government. They were meant for business. And having high-level languages in business could really, really accelerate the growth of business computing. He was noted for saying, much of my work comes from being lazy, which I think a lot of people in this room may be able to identify with. No. He said, I don't like writing programs. And so when I was working on the IBM 701, writing programs for computing missile trajectories, I started working on a programming system to make it easier to write programs. He was put in charge of a team to create an approachable language for scientific users of the 704, and they came up with something that they called Fortran. He also, for those of you who work on core or work on any kind of compiler development, you may have heard of the Backus NOR form, right? So that was a formal standardized way of describing computer languages that he worked on with, his name is escaping me, Peter Nor. And he was also part of the ALGOL team. ALGOL is probably the most important language that you've never heard of. Who's heard of ALGOL? Okay, so a lot of you heard of ALGOL. ALGOL is a really, really important language. It was designed to be approachable. It was designed to express logic in a way that was approachable to people who were not mathematicians, which is not particularly easy. And it introduced the first sort of lexical syntax. I know, you guys can see it on the screen, and you know it's coming, and you're excited, and I'm excited too. Begin. Open a file. Create an EBCDIC array. Yeah, an EBCDIC array. Create an EBCDIC array. Replace E by hello world. Write something out to that file, and end, right? So what do we have here? We have, we have a list separator, a comma, and all of these statements are terminated by a semicolon, and then the program is terminated by a period, right? So comma, semicolon, and period. Well, we don't really use the period anymore, because we don't need to put like program termination statements anymore, but we still use commas to separate lists, and ALGOL used the semicolon to terminate statements. So ALGOL gave birth to a language called BCPL. BCPL gave birth to a language called B, which gave birth to a language called C. And C is the grandmama of languages like Perl and Java and PHP, right? So I told you I was going to answer this silly question. Where did PHP semicolons come from? From ALGOL. John Kemeny and Thomas Kurtz. So John Kemeny is an interesting guy. He was born in Hungary, and like a lot of Hungarian mathematicians, ended up working on the Manhattan Project. So like all of these folks came over during World War II. He worked under Richard Feynman at Los Alamos. He eventually became a research assistant for Albert Einstein. He was one of the people that was responsible for verifying Einstein's calculations and making sure he wasn't making too many mistakes. His doctoral thesis on set and type theory, you may probably not ever read, but it probably impacts the code that you write every single day of your life. He joined Dartmouth after getting his PhD as a professor, where he met Tom Kurtz, who was also a professor there. The two of them collaborated as IBM research fellows. And they saw that it was really difficult to try and teach people to program using assemblers, because assemblers make sense to mathematicians. They don't really necessarily make sense to other people. So they were trying to create solutions for this complexity and make it easier to teach languages. Who was in Ed Bernard's talk on the story of Mel? Do you recognize it? It's the LGB30. This stupid computer just pops up everywhere in history. It's a really important computer. So they had this LGB30 computer at Dartmouth University, and this was just when Fortran was really coming out. And so they had this Fortran compiler, and they were like, what if we create a subset of Fortran for this computer? This like $27,000 computer with 16 instructions, and 4,096 words of memory. They tried to create a subset that would be really, really approachable to beginners. And they created a language called BASIC. So here's some more FizzBuzz for you. So this is a BASIC language. I tweeted this a couple years ago. I still have this book. This is how I learned how to program. So this is probably a generational thing. Who learned how to program in BASIC? Yeah. Who learned how to program in Python? Yeah. So probably younger people, or people who came to programming more recently, I should say. So BASIC is a really simple language. It only has 15 statement types. So you can assign variables with let. You can print. You can read. You have go-tos and go-subs. You can execute subroutines, define subroutines. You can dimension arrays. It's a very, very, very simple language. That changed the way we teach programming. And on those early home computers, so the TRS-80s and the Commodores, people in my generation who were learning how to program in the early 80s, this was our language. This is what you did before you graduated to Pascal. Okay, we're back to some folks that people might recognize. Dennis Ritchie was born in 1941 in the Bronx. Woo! And Ken Thompson was born in New Orleans a couple years later in 1943. They came together at Bell Labs. Bell Labs was located just outside of New York City. They went out into the world and they just kind of found really smart people and put them together in this lab in New York, outside of New York. Half of the 4,000 people that worked at Bell Labs had PhDs, and they just let them work on stuff. They weren't really required to improve the bottom line for AT&T. And with that funding, they were able to do a lot of really cool research. And they had been part of larger efforts to develop time-sharing systems, specifically this system called Multics, which was just huge and bloated and difficult to use. So they started working on something much, much more streamlined and stripped down called Unix, right? To play Unix is a play on Multics, right? Which was led by Ken Thompson, right? And the idea here was to create a system that used small programming modules, right? Well, they ported this to the PDP 1170 in assembler language, in the PDP 1170 assembler, and then a couple of months later decided they wanted to rewrite this operating system that they were building in a higher level language, right? So create a compiler for this. Create a compiler in this assembler and then use that to compile the operating system in a higher level language. They originally tried to do this in B, which I mentioned is a descendant of BCPL, but there were a lot of limitations in B. So Dennis Ritchie started to sort of refine B into a new language, which, because he's a very creative person, he called C. It comes after. So C is really, C is the most influential systems programming language in history. There's a generation of computer scientists who learned how to program. In C, it's only been in recent years that things like Rust and Go have started to make any kind of dent in the systems programming world. The internet runs on Unix and C, and it really contributed to the core philosophy of modern computing and modern software development. Make each thing do one thing well. To do a new job, build new, rather than complicating old programs by adding new features. Expect the output of every program to become the input to another as yet unknown program. Don't clutter the output with extraneous information. Avoid stringently columnar or binary inputs. Don't insist on interactive input. Design and build software, even operating systems, to be tried early, ideally within weeks. Sorry, Michelangelo. Don't hesitate to throw away the clumsy parts and rebuild them. Use tools in preference to unskilled labor to help lighten a programming task, even if you have to detour to build the tools and expect to throw some of them out when you're finished using them. Right? So these are some core tenets that we still use. This is the Unix philosophy, the Unix way of doing things. Another personal hero. You can probably see who he is because he's got his badge on. Donald Knuth. He was born in 1938 in Milwaukee, I think, and he went to Case Institute of Tech and got a PhD from Caltech. He saw computer science as this new field with no identity, and he was really interested in sort of analyzing the software itself and getting an understanding of how software is executed by machines, and came up with this science of the analysis of algorithms. So any of you who've sweated over a question about big O notation in a tech interview, You have Donald Knuth to thank for that. I'm sorry. But he's a really brilliant person. So he kind of pushed forward this science where you kind of look at the execution characteristics of an algorithm over some arbitrarily large set of data and see how the performance changes given that size. And it's important because if you have an algorithm that takes an impossibly long time to process some set of data, it's not a good algorithm. If you have an algorithm that takes an impossibly large amount of computing power or storage to process a set of data, it's not a good algorithm. So being able to quantify those things is vital to make sensible decisions about how to write a program. He also wrote The Art of Computer Programming, which is the best series of books you should buy and then give up trying to read. It's dense. It's dense. For a long time, like, he used to pay you $2.56 if you found an error. It's a hexadecimal dollar. Margaret Hamilton, 1936, she was born in Indiana. She went to MIT, developed software for predicting weather on the LGB30 under Marvin Minsky, right? She, like, when she came onto the scene, like, computer science and engineering were not in any way professionalized. They weren't even really taught. Like, you went to school, you were an electrical engineer or a mathematician, and then you, like, got into computers some other way. She said that learning was by being and doing on the job. As more people came on board, the more I became an expert and rose up through the ranks. A real-world system developed in uncharted territory. One could not have asked for a better research environment to set the stage for what would have come next and remain thereafter a lifelong career centered around developing more advanced methods. So she created things like formal systems modeling languages, system-oriented objects, domain modeling, automated lifecycle environments, lifecycle automation, open architecture, like all of these things. Oh, that's not even her, that's her. Were really pioneered by her work, and she worked on the Apollo program, which is super cool. Like, that's her inside of, like, the Apollo capsule, right, doing stuff. She joined the Apollo project. She was the lead developer for the software for the Apollo ship capsule thing. She programmed the computers that controlled the lunar module. An interesting story, the first lunar landing, 3 minutes before the landing, the computer became completely overloaded and started flashing executive overflow errors on the console inside, meaning that the guidance computer couldn't complete all of the tasks it had been asked to complete in real time, so it had to postpone some of them. But the computer software was smart enough to recognize that it was in this state and to remove non-critical tasks, so anything not involved in safely landing the lander, and reprioritize the ones that were critical, right? So critical path analysis and making sure that you clear the critical path so that it executes without being blocked by less critical processes. Like, this is important stuff. So, you know, it took guts and determination to get to the moon, but it also took a really, really smart programmer building really, really resilient and fault-tolerant software, without which the landing either would have scrubbed or those two gentlemen could have plummeted to their deaths on the moon, which would not have been super exciting. Edgar Codd is an interesting character. He was a mathematician who specialized in relational algebra and calculus, and these are kind of weird disciplines. He had this idea that any data can be expressed in the form of multiplicative relationships, right? He believed that you could access any data through relational algebra. And he tried to push this idea for a long time. He was at IBM. IBM made a fortune on this thing called IMSDB, this hierarchical database. He was really, really frustrated. He listened to Grace Hopper, who, you know, and didn't ask for permission. He asked for forgiveness. He went directly to IBM's customers and pressured them to pressure IBM to deliver a relational database, which they did, but because it was IBM and it was the 60s and they were all kinds of passive-aggressive, they just put other engineers to work on it without talking to Codd. And they came up with, they invented SQL, and they created some really cool stuff, but they did it really slowly, and they didn't do it as well as this other company called Relational Systems, led by a guy named Larry Ellison. They beat IBM to market with the Oracle database, which Oracle won. They did eventually come out with like DB2 and stuff, but it just never got to be what Oracle was. Codd spent a lot of his career battling against systems that were pseudo-relational. And then obviously the format eventually gained popularity in the 1980s and 1990s, and now, right, we all put stuff on MySQL unless we're running MongoDB because we're kooky. Tim Berners-Lee, he was a telecom engineer. He worked on typesetting software. He was born in the 50s in London. He's another Brit. He joined CERN in France in the 1980s. He was working on real-time RPC calls. At the late 1980s, 1989, CERN was the largest internet node in the world. There were all these things out there. He said, I had to take the hypertext idea and connect it to the transmission control protocol and domain name system ideas, and ta-da, the World Wide Web. Right? So he created this server on a Nextcube that someone had bought and didn't know what to do with. And after a couple sessions at the cafeteria, they decided they put this together, and they built a website on this machine. And info.cern.ch became the first website. It contained information about how to run your own web server, how to run your own browser. Unfortunately, the original site has been lost, but there are archives from like 1992 available if you're interested in searching for them. James Gosling, also born in 1955, he had a Bachelor's of Science from the University of Calgary. So he's Canadian, I think. And he went to CMU for Carnegie Mellon for his PhD. He worked at Sun Microsystems for a long time, where he and Mike Sheridan and Patrick Naughton got together working on a project to bring programmable set-top boxes for TVs in the early 1990s, which was a little bit before the time for that. But their project actually didn't die. It became Java. Java was modeled after C, C++. But the idea being write once, run anywhere. So like this really, truly platform-independent language architecture. It expressed 5 important principles. That code must be simple, object-oriented, and familiar. I think object-oriented, we can give that to Java. Familiar, okay. It must be robust and secure. Well, Java code, robust but secure-ish, right? Architecture neutral and portable, kinda. There's JVMs everywhere. You got JVMs in your phone, right? It must execute with okay, so 3 out of 4 ain't bad. It must be interpreted, threaded, and dynamic. Well, Java is definitely that. The last class of people I want to talk about, the interpreters. This guy on the left, Larry Wall, he started working on Perl at Unisys in the late 1980s. It was built around text processing with regular expressions, which kind of go back to Ken Thompson and the QED editor on Unix back in the late 1960s. It morphed over time to become a general-purpose language. They called it the Swiss Army chainsaw. It was the de facto scripting language of the web, of Web 1.0, essentially. Well, bouncing the wrong people. I bounced right over Guido. There he is. Guido van Rossum, born in 1956 in the Netherlands. He was looking for a hobby language to keep him occupied over Christmas break and came up with Python, which I think says a lot about Python. But it's a really easy and intuitive language. It's really powerful. It's open source. And the code is really readable. Like, if you say nothing about Python, it's pretty easy to read and reason about Python code. Now I'm going to bounce Rasmus. So this is some guy that I work with. He's aight. In 1995, he released some CGI scripts that he had written in C, which he used to maintain his personal homepage. Later, he extended these to allow database access. Released it as PHP FI, PHP Personal Homepage Forms Interpreter. A couple years later, Zev Sarasky and Andy Gutmans kind of got involved. They rewrote the parser. They formed kind of the basis of what would become PHP 3. They renamed it to PHP Hypertext Preprocessor because it was the 90s and like everyone was about recursive acronyms. Which was launched, I think, in 98. Someone in here will know this way better than me. And then they started a rewrite of the PHP core, which became the Zend engine. They founded Zen Technologies in Ramat Gan in Israel. And then this last fellow on the other end, some people may have feelings. This is Yukihiro Matsumoto from Osaka, Japan. He conceived this idea of Ruby in 1993. He was talking about creating a really powerful object-oriented scripting language that would be as easy as Perl and more readable than Python. I didn't get that backwards. But he created Ruby, and Ruby really revolutionized the web development scene in the kind of late 2000s, early 2010s. Because it is approachable and readable and extremely powerful, and is one of the true object-oriented languages. And they really created this this new generation of programmers who here is a full-time software developer and who's never compiled code. Yeah. 20 years ago, that was not a thing that existed. I want to finish, because this is community night, and I want to talk about community. I'm going to get personal, and I'm not going to cry. I want to talk about some of the people that got us here. It got me here, because I'm up here and I'm talking, so I get to do that. Sandy Smith ran the local user group when I lived in Washington, D.C., and he was really nice to me when I showed up at the user group one night after getting lost walking from the subway, and it was raining real bad, and I was overdressed and hot and sweaty and wet from the rain and really in a bad mood. But he was super, super nice, and we became friends, and I started going to the user group really regularly, and this guy named Michelangelo raffled off a ticket to PHP Tech 2013 at that user group. And I won it because I did, because of random chance. And I went, and I had been to lots of conferences earlier in my career, but they hadn't been really good or places I'd want to go. But I was like, whatever, I got this free ticket, and my company will buy me an airplane ticket, so I'll go and I'll see what it's like. And when I got here, or to Chicago, I met this guy named Davey Shafik, who I think saw that I was a lost little lamb and was like, hi, I'll be your friend. And we hung out that week, and he introduced me to someone who became the female technical role model that I had wanted my entire career, Sarah Goleman, who I saw gave an amazing workshop on building PHP extensions, and I was just like, I want to be you. Also at that conference, I saw a talk by Ed Finkler. He was giving his open sourcing mental illness talk in the Uncon track there, and I have major depressive disorder. I've struggled with it since I'm 7 years old. It's defined a lot of who I am as an adult, and seeing someone getting on stage and talking that openly about it changed the way that I really feel about public speaking. This guy also changed the way that I feel about public speaking. In that he really encouraged me to do it. He really told me, just do it, just try it, and see how you like it. And I did, and I started submitting to conferences. And this guy, Steve Myers, he is the team lead, PHP team lead for Open West out in Utah. But in 2014, he ran a conference called Ski PHP, and he accepted my talks. And they sent me out to Utah, and I went out there and I gave my very first talk at a conference. Which was amazing. And another person from my local user group, actually the Frederick user group, but he used to hang out at the DC user group more than he does now, was really cool to me and was really friendly and made me feel like I kind of belonged there. I spoke at Tech the following year, and I met this guy, and I don't know, he was like in a fight with, he was like a vendor, and he was in a fight with another vendor about whose shirts were softest. And I came around a corner, and he's like, aren't our shirts softer? And I'm like, yeah, I guess. And then he just used that to lord it over the other vendor, and I have held a hateful vendetta against him ever since. Now, if anybody's confused, I don't actually want to kill him. I don't. He's a good guy. But he's let me run this bit for 4 years, and I appreciate it. I also met Beth, who just became she was the second person that just kind of became the person I want to be. Her approach to education and communication, and just niceness, just her open niceness really changed and me and helped me be a better person. this fucking guy. I see him at all these conferences everywhere, and he really became one of my best friends. And I just had to mention him because I love him to death, and he's amazing. I'm pretty sure I met her before, but I did a lot of conferences for a couple of years. But at Midwest PHP in 2014, I think it was 2014, you probably saw her this morning give an amazing keynote. I was so blown away, like watching her talk about Git. I was like, oh my God, this woman is brilliant and funny and amazing and makes me think. Like every time I have a chance to sit down and talk with her for 10 minutes, she makes me think about things that I never thought about. And I'm so lucky to have a friend that just challenges my mind like Gemma does. And then I became friends with Heather, who some of you may have met while you're here. And she was really like my support group when I was becoming a mom, and became one of my very dearest friends. And Emily, who I met, I think at PHP Tech, I could be completely wrong, but it was just sweet and pure and nice, and let me stay at her house when I was in North Carolina and didn't want to be in North Carolina. And it's just open. And then I talked one time, I was still a new speaker, and I went and talked at a conference that was not a PHP conference, and I didn't know anybody was there. It was really, really scary. And there was one person there that I knew, and it was Lorna, and I barely knew her, but I think we'd been at a conference like one time together, so I was like, I know you. And again, I think she saw that I was a lost little lamb, and she was super nice, and hung out with me at this conference, and we had dinner, and she's someone that I really, really admire. She's brilliant, and writes really, really well, and speaks better than she believes she speaks. I don't know who that is. Cal is not the kind of person I ever thought I would be friends with in my life, but he is a sweet and genuine person, and cares so much, and teaches me to care more about community and to value all of the people that I meet on this journey. Sadly, he's not with us. God, that makes it sound like he's dead. No, he's not. He's fine. I mean, he's in Hoboken, so basically he's dead. Jeremy, I feel really responsible when I'm at a conference where Jeremy isn't, because it's like kind of the PHP community's backup clown. He really, like, he inspires me to let me be myself. And that goofiness is not always the worst thing in the world. He's also really smart. He's just ridiculously brilliant. And then, last but not least, this community, I met my person. And I think it's important. That's Graham Daniels, if you don't know. It's my Graham. We met at Sunshine PHP a couple of years ago and started dating at Midwest PHP in 2016, and now we live together and raise kids together, and I think about where my life is now compared to where it was when I got on the plane to go to PHP Tech in 2013, and all of these people that have come into my life, and this is a tiny, tiny subset of the people that have come into my life and changed it in so many ways. The person I was there is not the person I am now. And the person I am now is a much better person. And I owe that all to the people that I've met in this community. And I hope that you guys take this opportunity tonight, because it's community night, to start building those connections and making these friends and giving each other the encouragement to put yourselves out there, to make friends, to take risks, to fall in love, because it's really worth it. Thank you.
You may not have cried, but I did.